myself and our team. My name is Andrew Wang, and our team is Area 52. We are a FTC team based in Plano, Texas, and we have competed for a total of 5 seasons. This is our second season doing the STEM forum, and basically, we want to spread throughout our community by by doing these STEM forums. And to share a little bit about our team, uh, this is a little bit about our team. And I'll turn it over to Professor Yiping Wang. He's a professor of engineering at Collin College.
Okay, thank you, Andrew, for introduction. And let me share the slides. And also thanks for everybody attending in this Sunday afternoon. Okay. Um, Okay, so you guys will see the slides?
Yep, I do.
Okay.
Yeah.
All right, so yeah, I think I tried to make it a full screen. Uh, okay, so yeah, so the talk here today is future wireless technology and the AI convergence. So basically, we'll go through uh, several key points here. We'll look at how wireless technology evolved from the beginning to the end, and not to the end, actually, still evolving, right? So to present. Then 5G technology and path to 6G. And then we talk about the AI and the history of AI. And also we kind of look at the exciting future of AI and wireless technology convergence. So then at the last, we're talking about methodology approaches in the wireless system research. Okay, so um, here, basically, first of all, who invented the telephone? Okay, so we have a polling for the answer. So we listed the answer, possible multiple choices answer here on the slides. So first, 1, 2, 3, 4. Alexander Graham Bell, Alicia Gray, and Marconi. Okay, yeah. So please response in the chat. 47 or 4? Yeah, possibly. Okay. All right. So yeah, actually, it's a 1. Okay, so it's a bell. I think most of people did it right. So here is an article from EDN magazine, which published in I think 2019. So basically, tell the story of how this telephone invention happened. So Yeah, so there's a on February 14, 19, not 19, 1876, basically, on that day, two people filed the patents on the telephone, which, the design is similar. Everything is kind of, on the same page. So one is Bell. Bell's lawyer actually filed the patents on that day is in the morning, the recorded as the fifth uh, received on that day. And the Gray filed the patents on the 39th and the same day. So basically on the same day and the same invention. So there's a story, basically controversial story uh, in the article. If you're interested, this is the link here on the bottom of the right side. So basically, people say Gray is the first one come up with the ideas. But, according to the US patent law, so first to file rules and it indicates basically whoever filed the patents first, the rights will be granted to him. Doesn't matter, other people have the idea first. Yeah, but whoever filed it first is uh, have the rights. So that actually tells us a lesson. Basically, times is variable, important. So, so basically, we hope everybody use the time wisely. Okay, important things first. All right, so yeah, so that's a lesson from the history of the communications. All right, so yeah, and then about 20 years after the Bell filed that patent, and then Marconi actually proves the feasibility of the radio communications. So by sending Morse code wirelessly and basically transmit at one place and receive at more than 1 kilometer away. So so this is basically, proves the feasibility of the wireless communications. All right, so then after that, in 1947, cellular concept is born at the Bell Lab. By the way, Bell Lab is a powerhouse at the time in electrical engineering, right? So it was a branch of the AT&T. Right now is a part of Nokia because yeah, the Nokia merged with Lucent. Lucent was, AT&T formerly owns Lucent. So, but at the time, the hardware have a very limited capability in the hardware. Even though the idea is there, but there's no way to implement. Okay, so that's and also another issue is FCC doesn't allocate any frequency to operating those systems. Okay, so then at the 1958, Jack Kilby, I know probably a lot of people know him, and he's in Texas, in Dallas. Actually, it's a local here, working for TI. He invented the integrated circuits, right? So basically that will kind of lay the foundation for all the good things coming. Okay, so then 1965, Gordon Moore postulated in the Moore's law. Okay, so the Moore's law actually says every 18 months, the integration scale of these ICs will be doubled. So I believe everybody witness these things happening every day, right? So you see all the electronic devices with the advanced features coming out constantly. That's all basically thanks to these development of the integrated circuits. All right, so then, yeah, in 1972, Bell Lab, filed the first patent on the mobile um, communication systems. So I put basically, I have I put some of the title page in here. You see, this is a hexagon, type of a cellular system. So actually, these are kind of topology is still used now. Okay, so this is the history, and then after this, actually, I cannot. Okay. Yeah, about kind of less than 10 years after the Bell Lab patent, then the real system comes to the world. Okay, so that's basically the first G system. It is, come out in 1980. All right, so yeah, what is G here? So I welcome everybody. Select your answer in the chat. Number two, I guess, number one. Generative is the buzzword nowadays, right? So, yeah. Um, I don't blame you choosing number one, but the correct answer is number two, generation, basically. We have a first generation and the system in 1980. And basically, we have only voice call service available in those first generation system. And then, you know, the system evolves quickly. If you look at the trend here, you can notice every 10 years, right? So then the generation is basically elevated to the higher generations. So I think we're not going to talking about every generations, but some important milestone is from 3G to 4G. Actually, 4G is a 4G LTE, right? So basically, if you guys ever use the cell phone, LTE maybe on the corner of your top right side, right? So yeah, these are the 4G system. It is the first IP-based network. Okay, so before that, the system is all circuit based. Basically, it's called a circuit switch system. So what is the difference about the circuit switch and the IP network? IP is a packet switch. Okay, so circuit switch is you need a dedicated link to make the connection. Okay, so if you are in the conversation, so you occupy the link, nobody else can use the link. You will have basically dedicate the time for yourself. So this system is not efficient as a packet network, right? So packet network, you packets share the same link. You can transmit from one place to the other places. With some sort of minor delay usually it's acceptable. Okay, so yeah. So then another things is from generation to generation, the data rate will be increased a lot, right? So we are talking about, in some kilohertz at the beginning, now is megahertz and the gigahertz, right? So then, so for the 6G, actually, we are now is in the 5G, right? So if you are using the cell phone, some of our phones have a 5G there, and some of them still using LTE in some places. So the coverage is not, all over the places, right? So, but and now actually from the standards body, people are starting to consider the 6G. 6G will be comes to the market around 2030, based on 10 years per generation rules here, seems pretty consistent, right? So then, yeah, we'll be come to the market 2030. All right, so yeah. Okay, so then we have a next question is, what is the most expensive asset for wireless service provider? Anybody? Let me clarify what is the service provider. Is basically the carrier provides the wireless service for you, like AT&T, T-Mobile, right, Verizon. Those are the all service provider in the US. So number 4, operating spectrum. Number 1, antenna tower. Yeah, that's antenna tower is kind of expensive. Okay, so yeah, actually it is a 4 operating spectrum. So basically, spectrum is a most expensive asset, and usually the FCC will auction the spectrum when they kind of have the new system to the market. They allocated new spectrum, then everybody will like to jumping on that, get a share of it. So usually those spectrum, the price is in over $1 billion. Basically, tens billion is normal prices. Okay, so that's very expensive. All right, so yeah. Oh, sorry. This is basically, yeah, we are talking about, yeah, here supposedly you have a typo. This is we're talking about spectrum and modulation in the wireless system. Okay, so basically here is the whole range of the spectrum. So you see, the radio frequency is occupy only a small chunk of it, from like a 20 kilohertz to 30 kilohertz, no, to 300 gigahertz. Okay, so yeah, and then for other um, frequency, there are some other uses like a TSA, PET scan, yeah, and also some light, visible light is also there. Okay, so yeah, so for the um, 5G, actually, the frequency is um, up to 40 gigahertz, and the 6G will be in the 1 terahertz. So then basically will be expanded, will release a lot of spectrum to support the new services. So that's the spectrum. So why we need using the high band? So basically, this is the high band is basically more availability and also less interference, because not other things will be operating on those band. Okay, so that's the reason we will expand the band to the high frequency. And also another reason is you have a high frequency, your antenna size can be smaller to transmit those signals. Okay, that's the spectrum aspect. And then the digital modulation, that is something is important, is because the information getting crossed from one place to the other, it will be modulated to those symbols. Yeah, if you look at here, I listed several, constellation diagram of the symbols. So basically, these are the symbols is coming from the information bits. So you see here, we have 2 bits, 3 bits, and the 6 bits, right? So this is representing we have, if we using this kind of constellation diagram for symbols at our time, so then we can pack 2 bits. And if we are using the rightmost um, the constellation, you can pack a lot more bits, 6 bits, right? So, but you can see, the right-hand side, those constellation, they are close to each other. Okay, so they are very sensitive for the interference and noise. So some of the fading will be, make the arrow reception. So that's you have you need to make sure you're choosing the right modulation to transmit the signal. Okay, so actually, by the way, for the 5G, 6G, we are talking about 1024 uh, bits per symbol, which is very, very high order modulation. So you have a basically you can achieve a high throughput, right? So that's and also some antenna technologies. And these are the MIMO, multiple in, multiple out. So you can see here we have the information bits, and you divide it by 2 stream here, and the antenna will be transmitted independently to the receiver. The receiver will receive the 2 stream and then multiplex it together. Okay, so this is just the illustration. So in real system, those parallel stream can be like a 16, 8, something much more a number of streams is possible. Okay, so that's basically we achieve the high data rate, and also we could have a beamforming, and this is a kind of using those squares on a plant is basically antenna element. So using this antenna element, we can narrow the transmitted radiation beam in a very narrow direction to the design direction. So that way you can suppress the interference and also focus the energy to the design direction. Okay, and so for the 6G, actually they introduced a new feature called reconfigurable intelligent surface, and basically this is something which you can change the direction of the propagation of the radio signal. Like in this case, those are the surface can be mounted on the wall. You can reflect the signal into a design directions. These are actually has a lot of use, and especially incorporated with the AI. We will see, in the later slides. Another thing is the flexible air interface. We have basically here the air, on the air interface, we have a frequency domain and the time domain here. Okay, so this is the frequency domain, the bandwidth, and this is the time domain. So I would like to stress some important factor of this time domain. These are TTI, okay, that's a transmission time interval. It's an important parameter for the low latency transmission. Okay, so if you want to achieve a small latency, you need choosing a smaller, the shorter TTI. So that way, you can transmit the information quicker. Okay, so that's another things we need to look at it. Okay, all right. So yeah, here we wanted to those are the wireless aspect of the technology. And then we switch the gear and to look at the AI. Okay, so AI is nowadays it seems everywhere. So what is AI? Select the answer in the chat. So we have 4 machine learning, 1 deep learning, 2, 4. Okay, so yeah, actually, yeah, the correct answer is 2, to mimic the human intelligence in machines. Okay, so yeah, all these are deep learning, machine learning is a part of a subset of AI. Okay, so they are AI as well, but it's not the whole set of AI. AI, basically is more than just the deep learning or machine learning. Chat GPT is just the app, right? So using the AI technology. So that's a subset as well. Okay, so yeah, so in terms of the history of the AI, and we basically start from 1950, Alan Turing, basically known as a father of AI. He introduced a Turing test. Basically, it's a theoretical way to distinguish the humans and the AI. Okay, so that's, and then well, 1961, we have the first, industrial robot. It's kind of in the GM factory. So this is basically called a Unimate here. Okay, so this is the picture of it, and also in the 60s, actually, this one is a milestone, basically, Shaggy, and it is the first autonomous mobile research robot. Okay, so it's built in the Stanford Research Institution in California. So I think we're gonna look at this.
Shaky was the world's first mobile intelligent robot, embodying numerous breakthroughs in artificial intelligence, robotics, computer vision, navigation, and other research areas. The robot was developed from 1966 to 1972 by SRI International, then called Stanford Research Institute, and its legacy and impact are still very much alive today.
Shaky's really the great-grandfather of things like self-driving cars and even military drones. The hardware was really pretty primitive, but the software architecture and the software algorithms are what changed the world.
I think we all thought we were doing really interesting stuff, so it didn't really dawn on us that we were doing anything special.
Shaky established a position about what we should be thinking about as possible, as feasible.
To understand why Shaky is so important, we have to go back to 1966, and we have to understand where AI research was at that time.
Well, you have to remember that it was pretty much of a greenfield when Shaky started. All over the country and even outside of the United States, people were beginning to build the components to artificial intelligence. Nobody had tried at the time that Shaky was launched to integrate all the components of AI and robotics into a single moving vehicle that could reason about the world, could sense the world around it, and could take actions.
Prior to 1966, there were no robots, or at least not intelligent ones. The concept of an intelligent robot was limited to the realm of fiction.
You will meet a charming character in The Robot, always at your service.
When you read the title of the original proposal, it was something like a mobile automaton for reconnaissance. And the reason we called it an automaton was because until Shaky, you couldn't go to a funding agency and say, I want money to make a science fiction kind of device. So we needed a name. And finally, Charlie, in his inimitable fashion, said, it shakes like hell when it moves. Let's just call it Shaky.
Key components of Shaky's hardware were a TV camera to observe its environment, an antenna radio link, bump detectors, and a push bar to move objects.
My role was mainly get the images and get whatever coordinates they needed to determine where they were and extract the information from the image. I remember when I first saw it, gee, that looks like a dishwasher, on wheels.
While charming, Shaky wasn't impressive for its looks. It was the AI and programming advancements that made it famous.
We structured Shaky software in 4 distinct layers. And that was the first time that a layered architecture was used for robots.
Shaky's pioneering software architecture paved the way to a new era of AI and robotics. The SRI team later developed Flaky, a research robot that demonstrated fuzzy logic and goal-oriented behavior. Then came Centibots, one of the earliest projects in swarm robotics, where 100 autonomous robots demonstrated the ability to map a complex area collaboratively.
I like how it's code that isn't just turning numbers into other numbers. You get to see the thing come to life right next to you.
Shaky also inspired research in natural language-based interactions, leading to the popular speech-based technologies that we use today. Shaky's breakthrough in computer vision is now used to help drivers stay in their lane. And every time you get driving directions on your phone or a navigation system, you are benefiting from the A-star navigation algorithm, first invented for Shaky. Even NASA's Mars exploration rovers use navigational techniques that were first launched with Shaky.
The future is things like potentially having teams of autonomous aircraft that could go out, for example, and do firefighting, and doing this either fully autonomously or potentially in tandem with human-piloted aircraft that can go out and work with them collaboratively.
Shaky now resides in the Computer History Museum, visible to hundreds of thousands of visitors annually. And in 2017, Shaky was honored with an IEEE Milestone Achievement Award.
The Shaky milestone is important because, first of all, Shaky is the world's first mobile intelligent robot. In addition, this is the first IEEE milestone in the areas of either robotics or artificial intelligence.
Looking back, more than 50 years after the Shaky project began, it's inspiring to see how one small team can make such an impact. How one ambitious idea continues to benefit our lives. How one robot changed the world.
We didn't realize, I think, any of us, what the significance of this was. We knew we were the first, but nobody knew where it was going, and I don't think any of us would have predicted what happened.
Shaky planted the flag way out there, the model of the kind of ambitious projects that we should be looking at in the future.
Okay, yeah. Yeah, what ambitious project are you going to look at it? So it is, yeah, pretty rewarding, right? So at the beginning, you don't know the impact, but after like 50, 100 years, so this impact is huge. Okay, so yeah, let's move on to these AI, basically from the high level view of the AI. Basically, the definition of AI is to mimic the human intelligence, right? So then AI actually has a two broad category. One is a machine learning, and the other one is deep learning. Okay, so both machine learning and the deep learning kind of offers the ways to train the model and classify the data. Let's look at an example of cats versus dogs, right? So when you see a dog on the street, so how do you know it is a dog? I guess, chances are you see the dogs many times in the past, right? So that basically you have a lot of opportunity to kind of learn the knowledge beforehand. So then you know it is a dog. So basically the machine learning, and also you are telling the computer do the same thing as you are. And yeah, so that is kind of the process of AI, machine learning, and deep learning. Okay, so the difference is machine learning is you will extract relevant features from the data. Okay, so basically And then this is the predicting from the features to predicting the object. So this is a kind of like a, y equal to fx. So yeah, x is kind of a features and you corresponding to the object y. So these are basically kind of a mapping process. So for the deep learning, you don't have a knowledge of the features. Basically, you don't know. But in that case, you skip the process of to obtain the features. You just directly feeding the data into a neural network. Like here it's kind of like a neural network is similar to a human brain neural network, and you through the vast amount of data come in, and then to learn itself to kind of establish the right model. Okay, so these things basically works pretty accurate. I actually have a personal experience to share regarding this neural network, the human neural network. Okay, so I think a couple years ago, I went to Bay Area, basically. I wake up in one morning, basically, I suddenly got the double vision. Okay, so basically, my eye is not functioning well, and I always get a double vision no matter what. So I went to the eye doctor. I asked for some correction, and basically, but the eye doctor say, you don't need to do anything. You just deal with it, cope with it for a period of time, and your brain will learn to how to interpret those double vision become single vision. Okay, so yeah, that's actually, it took me about like a month to um, recover from the double vision. So basically, my brain is learned through the day-to-day life, and then back to the normal vision. So that's actually kind of like the human brain neural network is adapting the reality. Okay, so that's kind of an interesting factor, and yeah. Okay, so yeah, let's look closely on those AI technologies. Basically, we have two different category, right? Machine learning. Inside the machine learning category, we have this supervised learning, unsupervised learning, and reinforcement learning. Okay, so these are the three main learning method. So yeah, here basically try to summarize the difference. Okay, so here for the supervised learning, so you have knew the future, and also the target variables. Basically, you know the answer, and then you have the input goes through the model. You have a predicted output, so that predicted output will be compared with the expected output. Okay, so then if there are matches, basically your prediction is correct. If it is an error, then you go feedback to the model to update the model to make it better, right? So that's yeah. I think the example kind of similar to this is if you prepare for some of the tests, right? So maybe some of you guys prepare some important tests, and then you will study for some sample tests. So those sample tests usually comes with the answer key, right? So basically, you do the test, you compare with the answer key, and then if you did it wrong, then you learned what is the correct answer. Next time you will have a correct answer, right? So yeah, this is kind of similar to the supervised learning. Okay, so in that process, your supervisor is the answer key, right? So yeah, so then, basically it will help you to learn. Right, so then the unsupervised learning is kind of like you have the data come in, and then you don't know what is the future is, and yeah, you go through the model, you try to discover the pattern and identify the features, right? So just like an example will be, um, you bought a new video game, you try to kind of play with it, and you don't know much about how to play, but you just poking around, experience by yourself, or try to find the way to kind of navigate through the games. So these are kind of like unsupervised learning. And another the learning is reinforcement learning. This is a kind of like a using an example will be like if you train your dog to retrieve a ball, right? So you threw the ball in distance, the dog retrieve it, bring back to you. So you will reward the dog, right? So then, and the dog will learn, okay, so this is the right action to do. So after a couple rounds, so the dog will learn, what is the right action, what is the wrong action, right? So if it is wrong, then you feedback the penalty, right? So if right, you feedback the rewards. So that's basically kind of the reinforcement learning. So this is actually pretty suitable for the wireless systems. Wireless systems usually, at the receive end will have feedback, the acknowledgement or negative acknowledgement to the receiver. So that will make the receiver, the transmitter knows what is the correct parameter used for transmission. Okay, so that's relevant for the wireless systems. Okay, another main category is the deep learning. So deep learning, as we mentioned, you don't know much about the features of the data, right? So you cannot extracting the features from the data, then you just directly feeding into a neural network. So you have a multi-layer complex neural network. So these are kind of representing the layers. There's a link between layers, basically, to kind of come up with the algorithm to make sure you can classify it in the right way. So you have the output here. So in terms of the way the algorithm, you have different algorithms. The most popular one is CNN. Okay, it's the convolutional neural network, and this is good for spatial data, like images, right? So you have a 2-dimension, 3-dimension images. So that's basically using this CNN. And another algorithm is RNN. Okay, so it's a recurrent neural network. So this is a good for the sequential data. Basically, you have the relationship from the time to time. Your data has some correlation as the times goes. So this kind of a data you were using the recurrent neural network. So this actually for a lot of wireless systems, you have the signal is basically spent in the time domain, right? So you transmit it at a certain time period. So these are basically as a sequential data. So you will need using this RNN. All right. So yeah, then how we choosing what algorithm to use, right? So you have a machine learning, deep learning, which one we're gonna use. So really, it is depending on what the data you have, right? So if you're choosing the machine learning, so you have a knowledge of your data is well, you have a good knowledge about your data. Basically, you can have a label on the data, or you know the features of the data. So you'll be able to kind of test it out to see which combination of the parameter give you the better solutions. So then the machine learning is a good way. And for the machine learning, so your data sets, small is fine because you already have the prior knowledge of your data, right? So then also the smaller data sets will have, not require much computing power, right? So low computing power and a short training period time, right? So that's on the other hand, if you have not much knowledge about those features, the data sets, and then you will need to have a deep learning. Okay, so to perform better. And here is the review questions, and basically ask you a application with the good size of the data sets, but not much domain knowledge. Which technique should be used? Basically, domain knowledge is referring to the knowledge about your data, right? So your data is kind of your your target, the subject, right? So basically, yeah, two is correct. So you will need to using the deep learning, even though it requires the high computational power and larger data sets, right? So yeah, then the deep learning will perform better. All right, so yeah, here actually, so much for the AI. There's basically, the overview, and then we're talking about how the AI and the wireless can be converged. All right, so yeah, if you look at this 5G requirement, so this is a kind of it's published from the ITU, okay. So you have a triangle, okay? So basically, on each corner, this is enhance the mobile broadband. These are basically the bandwidth, the hunger applications like a streaming, video, and then massive machine type of communication. This is a kind of like the devices is just have a lot of devices needed. Example will be like a smart meter. Every house you need to have a smart meter, then reporting the readings of your meters, right? So these are kind of related to the smart city. And then those devices with the uh, um, you don't need a lot of data rate supported, but you need a long life, and also can be very simple, and also in most of the case it's in the sleep mode, right? So that's yeah, these kind of devices we're shooting for the low cost. And then another type is the ultra reliable and low latency communications. This is the use case will be like self-driving cars, and like you have a yeah, I think at the present probably all these self-driving car features are supported by the sensors, but later it's supposedly this ultra reliable, low latency communications will be connected to cars on the roads. Basically, if you have a car on the same roads, one car need to change the lane, then it will be kind of inform the adjacent cars and for the proper action, right? So then it will be kind of coordinated to kind of make the driving safer. All right, so yeah. And for the 6G, we'll be adding basically the communication capability in the space. So there are a lot of, you see here, satellites. You have LEO, MEO, and the geosynchronous orbit. Basically, yeah, those are the the satellites will be communicate, provided the link to communicate with maybe the plane. Also, you see here there's an inter-satellites link as well. Then you can kind of relay the information from the one region to another region, right? So that these are kind of make the connection and ubiquitous. Okay, so that's everywhere. So in that case, if we have the sensor, kind of using those network, then you can implement the sensor everywhere. So that will facilitate the AI application, being successful. Okay, so that is here is some of the application used for AI for wireless. Basically, the AI will be enhance the performance of the wireless communications. So yeah, we know wireless channel is very dynamic and sometimes faded, right? So you need a kind of estimated channel conditions constantly. Okay, so in that case, the pilot symbol is embedded into resources. So these are the resources. This X direction is the time, and the Y direction is the frequency. Basically, you embedded the pilot symbols in the certain density, and then those symbols can be feed through this deep learning machine, and then kind of make the channel estimation more reliable, more robust, so it will improve the system performance. Okay, and the other application will be the 6G RIS, reconfigurable intelligent surfaces. Basically, this is the surfaces, and then they have many antenna elements will be formed the beam to individual UEs, user devices, right? So then those are the beam forming. So basically, this is the deep learning machine. It will be output the beam forming, the weights, and to feed that RRS to kind of make your beam more accurate and increase the performance of the communications. And also they are kind of have the mechanism to feedback the reward. If it is very good, the reward will be feedback to the AI machine. Okay, so then basically, will part of the input for the deep learning process. This is a kind of like a yeah, it's a feedback of the reassuring the learning is working. Okay, and then this is some network management systems. You have the wireless network here, and then you have the AI is over here on the right, and then you output your AI decision and to here to control the wireless system. Okay, so here, actually you notice these are the two-way arrow, so you can feed the data this way and get the output of here. Okay, so that's basically another application for network management. We kind of short over time. So this is a smart city. Okay, so we have this is a functionality view. This is a network topology view. So you have basically these are the access points. Okay, so access points can be used as a sensor and communicate communication. So you have these two have both functions, and this one is only sensing. So basically, you have AI, engine here, and try to kind of calculate the best decision you needed. So this can be used in different ways. You have a smart living, smart environment. You monitor the pollutions. Smart living can be like the information in your home. I think you can have the refrigerator. You have a sensor in there to kind of monitor the stocking, groceries or something. Yeah, and the smart healthcare actually, this is interesting, right? So you have the learning machine to kind of gathering the information to provide the devices, the advices to the patient. So patient can be access the advice without the doctor in appearance. Okay, so that's basically very convenient. And also the sensor can be weared on the patients to provide the real-time data to contribute to the AI learning process. Okay, so yeah, I think they have a lot of other use of that. So we kind of are running out of time, so we just skip that. Okay, so in terms of methodology in the wireless research, so in the wireless research, actually, the key thing here is the channel is dynamic. Okay, so it will be up and down, change a lot. You have a propagation and the Doppler shift if you are moving at a fast speed, and then your channel will be changed, fast as well. Okay, so that's basically will kind of a challenge for the link keep the good reception level, right? So in this case, yeah, we have environment will contribute refraction, diffraction, scattering. So this is a kind of a contributed to the total effect of the wireless channel. So usually is modeled by the random process. Okay, so it is kind of a it's not a fixed constant, right? So yeah, in that case, we need a kind of a random Monte Carlo simulation. So basically, you generate a random number for the channel conditions, and then do that, repeat it many, many times, usually, thousands and 10,000 times to generate the statistic meaningful results. So that's the approach usually we are using. Okay, so that's a very computational time consuming. Okay, so yeah, then in terms of the simulation, we have a link level simulation, which you simulated the link from the transmitter to the receiver. You have a certain process and also go through the channel, and then at the receive end, you receive the signal, try to decode it, right? So then, yeah, here is actually one of the research project my student did actually, a few years ago. There's the Collin College kind of here is the signal noise ratio. This is the bit error rate. Okay, so to kind of quantify the performance, of course, the bit error rate is lower is better, right? So then we are look at the different channel coding rate to kind of estimate the bit error rate. And another type of research simulation you can do is the system level simulation. Okay, so in this case, we have a hexagon type of cell, right? So we drop the mobile, and we assuming the mobile moving around at a certain speed, and then kind of generate some sort of a traffic. Okay, so then try to estimate the performance, basically, the throughput, how many, what's the data rate that can be achieved. So these are basically, if you look at this, is a cumulative distributed function. Okay, so these are all representing by those probability type of results. This is because the nature of the wireless channel is kind of not a constant. It's have a behavior of the random process. Okay, so yeah, I think that's conclude my talk. And any questions? Yeah, you can unmute yourself if you have questions.
Yes, Mr. Wang, I just have one question.
Yeah.
Is there perhaps any projects that you guys are working on that we can go ahead participate also just to start building our portfolios?
Yeah, actually, right now at we have one wireless project starting at the beginning of this semester, and yeah, it's ongoing and already ongoing. Usually we accept the new student, yeah, at the beginning of the semester. But yeah, my time is limited, so we only kind of accommodate whoever is a Collin student, basically. You have to have a, register in the Collin class, then yeah, we can talk.
I see, I see. And how do we join those research teams?
There's a Casman's. Yeah, well, I will post it on the web, on Canvas. Okay. Yeah.
Okay, perfect.
Yeah. Yeah, I think that Eric asking, would the digital simulation be both deep and machine learning? Yeah, we have some project involve this AI. Actually, we kind of have an application go with the robot actually to identify those parts and try to classify which pins need to go, right? So these are kind of like a autonomous manufacturing kind of situation. Yes.
Professor,
Yes.
so is there any concern about, if I'm understanding it correctly, the AI and the wireless system being used for smart city? Is there any concern about the foundations that the AI is building on to be
Open?
not open but wrong, and start applying those things into, like you had on your PowerPoint there, you had, governance, healthcare. At one time, the food pyramid was taught as the the way to follow to be healthy, and now that we've been better informed, it's starting to change. So, will I guess will we be able to go in and kind of tweak the foundations of this AI learning?
Yeah, okay, so I get your point. Basically, the AI is just the tool. And whatever the human try to kind of use it for some purposes, you basically your foundation has to be right, right? So the underlying assumption or whatever the foundation has to be right. If you are based on the wrong foundation, then the results come out most likely is not helpful, right? Yeah, I kind of agree with you. Yeah, yeah. I think yeah, Joseph asking the cell can be smaller. Yeah, I think nowadays actually it's tended to be the cell tended to be like a micro cell, pico cell. Those are much smaller than a conventional cell, which like the radius is kind of several kilometer, right? So we are talking about the cell will be very, very small. Actually, that fit into the spectrum. Actually, new spectrum introduced is at a very high frequency. So if you notice, if you notice the higher the frequency, the more path loss you're experiencing. If you go through the same distance, basically your path loss is bigger if the frequency is high, right? So that's yeah. In the future, the cell is kind of a more uh, small cell is more popular, and also we probably have a mixed situation. You still have a big cell to have a big coverage from the mobility perspective. Big cell, you will have a less like a handover, right? So yes, it saves some signaling, and but in terms of the reception, you probably have a small cell, and then to kind of have supported your data rate, because those small cell is close by, right? So you can support them more throughput.
Hi.
Actually, it's yeah. The question is, will RIS begin to replace the antenna placement? Actually, it's not. Antenna is from basic. If you have 2 points, right, transmitter and then receiver, so you still have a originating antennas, right? So this is the RRS is something like in the middle, considered as a repeater type of functionality. If the propagation environment is very harsh, and then you have your signal attenuated very quickly, so it kind of used as a booster, right? So basically, boost your the signal can go longer. Okay, so we'll have one more question. I heard somebody try to ask
Yeah.
some.
Yeah. Professor, I have a question about what is the difference between the statistics and AI? It sounds like even the statistic is also collect the data and try to make analysis and set up model and use this model to predict something.
Yes. Statistics is basically it's just the halfway. You collected the data, you kind of come up with some characteristic of the data sets, like you know your computer, the average value, the variance, right? So kind of a standard deviation type of things, and then you know the distribution. But it really doesn't kind of generate any action per se. But the AI actually can generate some sort of you know action command to kind of direct you to achieve a certain goal.
Okay.
All right.
Thank you.
You're welcome.
Mr. Wang, I have one more question. We spoke about also how we're going to implement 6G network, and then we also saw the frequency spectrum, and then we know the higher the frequency, the higher is the power as well, right? So at what extent are we going to extend the 6G network in the frequency spectrum?
And what
At
you
what
talk
extent? At what
what
extent are we going
extent?
to extend the
Yeah,
6G network?
it will be it yeah it will there's no limit. Basically wherever it's needed, right? So it's kind of a you know the 6G is uh complement to the 5G and basically extended to the higher frequency and basically you know when the needs high, the demanding is high, then you are well running out of the spectrum, right? So then kind of you need some green field of the sets of the spectrum available for the new applications. And also another thing is kind of like the satellites is a big thing for the 6G. Actually, you know the satellites communications. Basically, you know you're talking about nowadays. Actually, a lot of companies try to kind of you know try to um, deploy the satellites on orbit. So whoever occupy first, you will have the territory. So this is the things people are kind of you know looking to kind of occupy the territory first.
I see. Thank you very much, Professor.
All right.
Okay, so we're going to be ending the STEM forum. Thank you for everyone for attending. And if in December, we're going to hold another one about AI and healthcare. And if you would like to attend that, be sure to sign up for it in an email that we'll be sending out within the next 1 to 2 weeks. And also, if you're from Collin College, make sure you leave your full name in the chat if you would like to receive credit. And lastly, if you haven't filled out the form, please fill that out. I'll send it in the chat again. And just thank you for everyone for attending this meeting.
Yeah. Thank you.